have already the minimum number of bits to represent the messages. So that's a good assumption that I'm justifying here for just looking at the likelihood function. Then you can avoid the math also. And so you'll see maximum likelihood detector is basically used everywhere in communications. We always assume that the inputs are equally likely. Now, either for the map detector or for the maximum likelihood detector, which are often the same anyway, there's a concept of a decision region. And a decision region, DI, in words, is defined this way. It's the region of Y values, Y could be continuous or discrete, that the map or the ML, sorry to use the pun here, map, which is not maximum approximation, but actually map, like mapping, maps to m hat equal to m sub I. So we're going to see a set of Y values. In our example earlier, we saw these two Y values map to 1. So that would be the decision region. If it's 3.9 or 3.1 or 2.9, it maps to 1. If it's minus 2.7 or minus 3, it maps to 0. I could have a continuous type of output. So I'd have regions of Y values, which would all map to the same decision. I see anything in that region, my optimum detector tells me decide message Xi. And I would have a decision region for each and every message that's transmitted. So it's a way to carve up the output of the channel and say, okay, I see V values or Y values in a certain region, then I decide those values. And those regions, of course, are specified this way. It's all the V's for a given message I such that this is true, greater than or equal to P of Y given X of Vj, Pxj, for all, that's what this symbol means, j not equal to I. So in other words, it's basically the regions of Y for which that particular value of X, indexed by I, is most likely or maximizes the a posteriori probability. So if I had a continuous variable, because maybe I had continuous noise, like Gaussian noise, being added to a signal, it may be that I have 4 symbol vectors that kind of look on the output like this. If I had noise added to them, the actual symbol values themselves are like this, but noise may have some kind of distribution, so it'll skew. Okay, my demodulator is going to see some of the noise. That's going to affect my Y value. And I may find out for the given probability distribution that I see that the decision regions basically look like this. I see a Y value anywhere over here in this kind of semi-quadrant or decision region for symbol X1, I decide message 1. If I see any value over here, I'll decide X3 and so forth. Now I could always carve up my receiver demodulator output space, if you will, into decision regions. And that would be a way to implement simply the optimum detector. Y falls in this region, okay, I know that that corresponds to a particular message. Falls in another region, it's the message for that region. So these decision regions we'll see we'll use heavily as we actually get into more examples later. What I'd like to do now here in the last 5-10 minutes is set up why we can get away with that vector channel. I asked you momentarily earlier to accept the vector channel output. Irrelevant channel components. What parts of the output can I throw away without any loss? And so there's this famous theorem on irrelevancy that basically tells you when you can throw away outputs from a channel because they don't help you decide which message was transmitted. And we're going to take our vector Y at the output and we're going to separate it into 2 parts, which may in fact be vectors themselves. We'll call them Y1 and Y2. And we would like to see, can we ignore Y2? And we're looking to see which components of the output we can get rid of if you will, in the receiver. Okay, and the theorem goes like this. If P of x given y1 and y2 is equal to P of x given y1, okay, that's almost trivial in a statement, then I can ignore y2. And that would allow me to throw it away because y2 is not really there any longer in deciding. Now this can be restated using Bayes' theorem. y2 given y1 and x is equal to P of y2 given y1. So there's some algebra, but you can show that this second line, which is a little easier to work with, okay, it is equivalent to this first statement. Then if this is true, y2 is irrelevant. Why is that second line a little easier to work with? Because you're getting conditional probabilities that look more like the channel description themselves. P of y2 given py1 and x is equal to P of y2 given y1. Then basically there's nothing new about x and y2. y1 is sufficient to represent everything I would want to know about x, namely when I could decide with minimum probability as to what message has been sent. Let's look at some examples of this. You can look in the notes for the mathematics behind it, but that's the basic term. How would we use it? And there's some nice friendly examples here that illustrate the point. Suppose I have transmitted signal x, and this is essentially what my vector channel does. It adds noise to x, N1, and it produces an output y1, and I have more noise, N2, that produces y2. Okay, and this noise here, N2, is independent of noise N1, and as well as independent of x. Now, it's almost trivial. I could throw away y2 there. And you look at that and you say, well, that's just extra noise. Who needs that? Okay, it's uncorrelated with everything going on. Throw it away. Well, also, it's very easy to say that P of y2 given y1 and x is the same as P of y2 given y1, which is the same as P of y2, which is P of n2. Okay, so in all cases, that's that probability distribution. So that follows directly. This is going to be kind of interesting because when we prove that the demodulator is sufficient for the additive white Gaussian noise channel, we're basically going to get this. We're going to get some noise components that are added to the signal, and then we're going to get noise components that are added to basis functions which are outside the set we're looking at, and those are irrelevant to the decision, so we can throw it away. For the additive white Gaussian noise channel, that's basically how the proof goes that we can use that demodulator. All the noise we missed is on basis functions that have nothing to do with the transmit signal and are orthogonal to them, so throw them away. Independent noise, throw it away. Maybe not so obvious. Another way of using this theorem is to add noise to the signal, pull it out at that point, call it y1, add some more noise to the signal n2. Call this one y2. Perhaps not as obvious in this case because y2 has some information about x in it, clearly. It has more noise than y1 has. But if n2 and n1 are independent, one can show that P of y2 given y1 and x is equal to, well, let's see, if I'm given y1 and x, and I'm looking for y2 here, this is going to be P of noise 2 evaluated at y2 minus y1, because I'm given y1. And that would be the distribution for P of y2 given y1 and x. Now also, P of y2 given only y1 is the same thing, because I only need, and since those two are equal, throw that away. Don't need it. Okay, so adding more noise, just making it more noisy, doesn't help. Okay. So that's an irrelevant component. Throw it away, receiver. Don't need to try to deal with that. That's not going to help you in terms of an Optum decision. One more example. Got a signal X, and I add some noise N1 to it. I'm going to write it like this. And I produce a signal output Y1. And then I also take some independent noise, and I add 1 to N2, and I call this Y2. Now you look at that one and say, wow. Heuristically, your tendency to look at that and say, wow, noise plus more noise. I just showed that if I had the X and I added some noise and I added some more noise to it, it didn't help. In this case, it looks like I've got the noise and I add some more noise to it. How is that going to help me? I don't even have any X in there. But in this situation, it's not irrelevant. No matter how hard you try, you won't be able to get that expression that I just showed you, P of Y2 given Y1 and X, to be independent of X. It doesn't happen. Okay? And Y2 is not irrelevant. It is relevant here. Can't throw it away. Anyone want to tell me why it's not irrelevant here? How could you use Y2? How could it help you? That's right. Suppose N2 was really small, for instance. So N1 was dominant here. Now I have the noise by itself, so I'd subtract that from Y1. I'd have almost no noise in the system. So in this case, it could help me. The condition is not met. So the noise is relevant in this case. Okay, so we're right at quarter two. We have one little tiny thing that is an application of this theorem of irrelevance, which is called the reversibility theorem, which basically says if you run the output of a channel through a one-to-one transformation, you don't lose anything. So if you've got a convenient one-to-one transformation, it makes your detector easier to implement, and you can do it. And the input to that one-to-one transformation is irrelevant, is what basically that theorem is. So it's kind of a simple example of the theorem on irrelevance. We'll begin with that in next Tuesday's lecture, and then we'll begin to get into some of the more sophisticated topics related to additive white Gaussian noise and why can we throw away all that noise that's not represented in the receiver demodulation vector. So that will be Tuesday's lecture. So everybody have a good weekend. And please do try to take a homework look at that early, especially if you're taking a quals next week. See you later.